Our next speaker is Max Bremmer. He's from the University of Texas. His field is in computational science, engineering, and mathematics. His advisor is Clint Dawson, and he did his practicum at Lawrence Berkeley National Laboratory.
Great. Alrighty, thank you everyone for being here. I kind of want to talk about kind of the crux of my PhD thesis, which has been porting our shallow water code onto a task-based runtime. In our case, this is HPX. And I thought since the audience is kind of so broad here, I really kind of wanted to talk about kind of what are the intuitions for making sure if this is a good option for you, and what would kind of be a set of questions that you should ask yourself to figure out if it makes sense for you yourself to move towards a task-based runtime. So I just want to begin, what are the things that make code slow? And this is actually an acronym that the HPX people use. And they say the 4 things that make parallel code slow. Well, first off, it spells out slow. So it's starvation, latency, overheads, and waiting on contention resolution. But they're the 4 horsemen of the apocalypse. So if you think about your application and try to scale it out. And if for whatever reason it doesn't scale out, it's probably going to be one of these guys. So just for example, starvation, it might be that your machine isn't actually able to have enough flops. You have cores idling, and so if you're scaling out, you're adding more cores, it's obviously not going to be helpful. If you have a fairly optimized code, and these factors are still a problem, I would recommend the runtime solution. So the runtime solution says that trying to come up with ways to more efficiently give your machine things to do becomes increasingly burdensome. So once you have to deal with all this kind of asynchrony, less synchronized code, it can be very burdensome. And at some point you say this is not like a good place for a domain scientist like myself to spend their time. And this is where people say you should inject a runtime in there. And the idea behind a runtime is that you want to be able to abstract your code as kind of a set of tasks and dependencies. And these, in turn, will then be given to the runtime, and then the runtime will kind of do all of the resource allocation and make sure that everything runs efficiently. This is super popular right now. There's a giant ecosystem of runtimes. Legion and Charm++ are maybe kind of, I think, 2 of the most popular ones. We're using Stellar HPX, so there's actually 2 HPXs. Ours is being developed by the Stellar group at LSU. This is It's a fairly mature project. There's a large group of international developers. It's 350 lines of C++, and they've done some big runs. But since this is also abstract, I just kind of want to give you my case study. So I'm looking at hurricanes. So we're particularly interested in kind of mitigating the effects of hurricanes. So hurricanes, incredibly devastating natural disasters, very costly. If you have kind of means to predict where kind of the brunt of those events are going to make landfall, that's something of value. And so this was kind of a collaboration between the Stellar group and a bunch of coastal engineers to try and figure out what would be the benefits of moving towards a task-based runtime. The actual thing that we're interested in solving, so the computational kernel, is we end up with plots that look like this. So we're solving the shallow water equations. Kind of the most costly, devastating thing during a hurricane is actually the surge. So it's actually a tsunami-like wave that gets pushed onto the coast by the winds, and then you kind of have restitutive forces of gravity and friction that are kind of holding that back. But we're solving the shallow water equations. We're using a discontinuous Galerkin finite element method. Those are just words if you don't know what that means. But you should really just think of it as an explicit stencil kernel. And I'll actually show you some pseudocode. So I'll show you what this is actually looking like. And then here's some talk about irregularity, but I want to talk about that a little bit more later. So the algorithm is, I would say fairly straightforward if you understand, a stencil code, something like heat equation, something like that. Basically, you have a mesh, you partition it up, you chunk it up, and then you're going to post all the sends and the receives associated with kind of halo zones that you need. You try to do as much internal work, and then you wait for the sends and receives to complete. So in kind of an MPI implementation, we would do this with isends and ireceives, and then we would kind of sit in a wait all call there at the end. And this is where the code would idle. Alternatively, what you would do with the HPX runtime is it looks exactly the same, except when you return, you actually return kind of a future to these messages being received. And so when you do this, you actually cede control back to the runtime. The runtime might be running lots of these meshes on a node, and it might be able to find one for which these messages have arrived and be able to do kind of the subsequent step, kind of process the message and then do the Runga-Kata updates. And when that then finishes, it might be that the messages for the first submesh have arrived. And so in this manner, you're kind of naturally giving rise to something like WorkStealing. So hopefully, you know, the core is busy all the time, even though you might have to be waiting on messages. So the first question that we have is a performance comparison with MPI. So this is actually a very regular problem. So this is not a super good use case for task-based runtimes. But it is kind of, I think it does convey kind of one of the key important intuitions. So I've actually taken that algorithm that I've just shown you. I've implemented it both with MPI and HPX. And so what you can see here is the orange line kind of at 60%, parallel efficiency is MPI. There's actually a good reason for that. That should actually be a little bit higher, but I don't want to talk about it anymore. And then the other one are the HPX things. And you can see that HPX actually isn't scaling super well. And I would argue that this is actually expected. So what happens is HPX provides kind of much more fine-grained control over which tasks are being run when and where. And what happens actually is that task overheads are starting to kill you. So HPX itself is actually not immune from the four horsemen. And this is actually kind of the first bit of intuition I want to give you about task-based runtimes. Task-based runtimes do come with overhead if you're not careful. And so you need to figure out actually what is the task granularity that you need to be able to run at to kind of ensure that you're spending most of the time doing useful work. So this is, you know, a very important thing. It's also very architecture specific. So you also have to be able to kind of maintain a lot of control over your task granularity. And then just kind of as an aside, you can also do weak scaling. So it's not that HPX just doesn't scale, but it's really that once the task granularities are correct, HPX will scale very well. But if they're not, you're going to spend most of the time dealing with overhead. So that's kind of the first bit of intuition I wanted to give you. But something I mentioned earlier, right, this wasn't a super good application. Everything's very regular. There's not a lot of starvation. MPI is very fast. And so you wouldn't actually expect to see kind of large numbers of benefits. So now the next thing that you should really think about in your application are what are kind of sources of irregularity? What are things that might cause the application to spend more times in certain parts of the code than others? And for hurricane storm surge, one of the key issues is wetting and drying. So when you're simulating a storm surge event, you have kind of the land and then the ocean is going to come onto the land. And simulating dry regions requires no computational work, and we have to kind of do the full physics for the wet part. And so you actually see this. This is kind of the static partitioning. So this is what we were doing beforehand. The plots are computational intensity. So for a given rank, what fraction of time is actually being spent computing? So white basically means it's running, everything's great, and dark means that those cores are idling. So this is something we'd like to avoid. Just a side note, these are actually simulations of our code. So this is actually, we built kind of a discrete event cost model to kind of do these analyses offline. But yeah, and this was also part of my practicum work. But what you can see basically in the static case is that you're simulating, the storm makes landfall, you get all this inundation, and you kind of have this dynamic load imbalance. So these task-based runtimes actually provide mechanisms to dynamically reallocate these submeshes on the fly between nodes. And so this will actually then allow you to kind of achieve these compute utilizations on the bottom. So that this semi-static and asynchronous diffusion approach are approaches where we're actually throughout the simulation redistributing meshes across the cluster. And so you can achieve kind of much better utilization in these use cases. Another kind of thing that we're looking at right now, and this is something that I'm actually really excited in, is adaptive local time stepping. So for these explicit stencil codes, the stability constraint that you typically have to respect is the CFL condition. So the CFL condition very roughly somehow tries to limit the amount of distance a wave can travel through a cell in one time step. What I have here is a kind of space-time plot. So I'm solving Berger's equation just for the sake of simplicity. On the x-axis, I have elements, or this is kind of the spatial domain. And on the y-axis, I have time. And what this equation is actually simulating is you have a rarefaction wave. So you have two waves moving apart, and you have thinning in the middle. And what happens then is in this thinning in the middle, the wave speeds slow down, so you're actually able to take larger time steps. So you can kind of see here, in the middle, you're able to take fewer and fewer and fewer steps as the simulation progresses. And so this is something where achieving, so there's a few things that actually make this complicated. So one is that the time steps actually depend on the solution. So you need to know your solution before you can actually generate the task graph. So these are very, this is kind of something that would be very hard to kind of program efficiently with something like a parallel for construct. But yeah, so this is kind of something that we're looking at. I think, well, I'll get to that in the conclusions. So just for the conclusions, I think the takeaways that are really important is working with HPX was very comfortable. It feels like the right level of abstraction. The kind of futurization framework that they provide feels very correct. The Stellar group was also very good to work with. There is kind of a lot of, there were issues that came up, and they were kind of very receptive to bug requests. And I think whenever you find a library where developers are kind of willing to make sure that their users are happy, that's always a good thing. The things that I didn't want to put into bullets are the software engineering effort was a little bit intimidating. So I think often people are very kind of hesitant to kind of adopt these task-based approaches. The refactoring that we had to do actually coincided with a lot of refactoring that we were doing anyway, kind of trying to be more consistent with best software engineering practices. So yeah, I think the questions you should ask yourself if you want to port your application to a task-based runtime is actually profile the code and figure out what are kind of the speed-ups you would expect. So often people think, this is a bottleneck, but you should actually really profile it and see, how much is it slowing down your code, and try to come up with performance estimates. Because for some people, something like a 40% speed-up would be fantastic, and for some people, they won't lift a finger until you're talking order of magnitude speed-up. I would say don't underestimate the software engineering efforts. I was talking about this a little bit before, but this for us was a lot. So the old code was an old Fortran code. There were a lot of global arrays. We had to mess around with a lot of stuff. We had to refactor a lot of that. I think you should refactor your code anyway if that's kind of the situation. So I think programming for a task-based runtime kind of very clearly indicates intent. And I think that kind of makes your code more readable and will probably just make you happier in general. But it is a lot of work. So don't expect to just, plug in a different library and expect to see it speed up. And then the last thing that I wanted to talk about is for application developers. So I think often the computer science people come at this and say, we can make your code run faster. But what they're not often looking at is, are there ways that we can run different algorithms? And so I really like the Ludwig Wittgenstein quote where he's talking about the limits of his language mean the limits of his world. And I think when you really start thinking about programming algorithms in a task-based paradigm, that you can really start extracting more opportunities to take advantage of adaptivity. And so from kind of a mathematical perspective, I think this is really great. So I think there's kind of in a similar way to quantum computing, I think there's kind of a new class of algorithms that will hopefully kind of come out of task-based runtimes. And I really hope that it's kind of at this interplay of a new programming paradigm and kind of mathematicians looking for better ways to come up with approximations. Just to conclude, I'd like to thank my advisor, Hartmut, who's one of the lead HPX people, and then my LBL advisors who have worked on a lot of this. And actually, my whole PhD thesis kind of turned into this after being inspired by them. And then obviously the DOE CSGF. I mean, this has been a wild journey, and I definitely would have not been able to do this without the CSGF support. So with that, I'd like to conclude and take any questions.